Okay, so today we're going to be taking a look at Lesson 19, the Euclidean algorithm as an application of the long division algorithm. So our opening exercise here for the classwork, Euclid's algorithm is used to find the greatest common factor, or GCF, of two whole numbers. Euclid was a mathematician a long time ago, and he created this algorithm in order to find the greatest common factor. So the steps to do this would be to divide the larger number of the two numbers by the smaller one. Then, if there is a remainder, divide it by the divisor. Continue dividing the last divisor by the last remainder until the remainder is 0. The final divisor is the GCF of the original pair of numbers. Okay, so that might sound a little bit complicated. So what we're going to start off with is a little bit of review of long division. So for example, we have 383 divided by 4. Okay, so our first step, we see we have 300 divided by 4. Okay, so we're going to put a 0. Now we have 38 tens divided by 4, which we know is going to be 9. 9 times 4 is 36. Okay, and then we have 8 minus 6 is 2. And we can bring down our 3 ones. So 23 ones divided by 4. Okay, that's going to be 5. And then 5 times 4 is 20. We subtract, we get 3. Okay. Now we know from our work with divisions that we can continue by moving over to the decimal place. So now we have tenths. So now we're going to regroup as 30 tenths. So 30 divided by 4 is going to be 7 tenths. 7 times 4 is 28. And then 30 minus 28 is going to be 2. Okay, and then we move to the hundredths place. We bring down our 0. Now we have 20 divided by 4 to get 5. Okay, and then 5 times 4 is 20. We are left with 0, okay, as a remainder. So our answer here is going to be 95 and 75 hundredths. Okay, moving on to 432 divided by 12. Okay, so now we look at 43 divided by 12. It's going to be 3, so 3 times 12 is 36. 43 minus 36 is 7. We bring down the 2. So now we're left with 72. Okay, and we know that 72 divided by 2 is going to be 6. 6 times 12 is 72. We're left with 0 as a remainder. Okay, and then last we have 403 divided by 13. So we start off, we see that 3 times 13 will get us 39. 40 minus 39 is 1, and we bring down the 3 ones. You can see that's going to be 1, and we're left with a remainder of 0. Okay, so just some quick practice and review on how to do the long division algorithm. Now let's take a look at Euclid's algorithm conceptualized with a model. Okay, now the opening exercise was meant to recall how to determine the quotient of two numbers using long division. So you've practiced the long division algorithm many times. Today's lesson is inspired by Euclid, a Greek mathematician who lived around 300 BC. He discovered a way to find the greatest common factor of two numbers that is based on long division. So if we take a look at our first example here, we want to find out what is the greatest common factor of 60 and 100. So looking at the way this models out, we're trying to find the GCF of 60 and 100. So we can set this up like an area model. And we want to make the largest size boxes as we can without any overlap or anything extra. So notice that we can use the GCF of 20 to create the largest square tile that covers the rectangle without any overlaps or gaps. So we use a 20 by 20 tile. Okay, so 20 is the greatest common factor of 60 and 100. But what if we didn't know this? We could start by guessing. So what's the biggest square tile that we could guess? Well, if this is 60, that's where we're going to start. So if we think about shading in 60 tiles, okay, in both directions. Now, this will fit But the problem is there are 40 units left over. Okay, so 20 and 20. So if we do the algorithm, this will prove it. So if we think about 100 divided by 60, it'd be 1. And then we have 40 as our remainder. So the leftover area is going to be 60 by 40. So you still have your 60 over here, and then 40 will be over here as these two spots. So now we think, what's the largest square tile that we can fit in the leftover area? Well, in this case, it's 40 by 40. Okay. So now we shade in 40 by 40. I'll shade it in a slightly different direction so we can see how it's different than our first step. So now we look at what is the leftover area. So the leftover area now is 20, and we still have 40 over here. So now we think, what's the largest square tile that we can fit in the leftover area? So in this case, it's 20 by 20. So we think we're doing 40 divided by 20. We have a remainder of 0. So when we divide 40 by 20, there is no remainder. So we have tiled the entire rectangle. If we had started tiling the whole rectangle with squares, the largest square we could have used would be 20 by 20. So now let's take a look at example 2 as to how to apply this. So let's look at Euclid's algorithm to solve some of the problems from our last session. So what is the greatest common factor of 30 and 50? Well, we know from our work in lesson 18, okay, that the GCF of 30 and 50 is 10. Okay. Now we take a look at using Euclid's algorithm. We follow the steps that are listed in that opening exercise. So what we're going to do is we're going to divide the larger number by the smaller one. So in this case, we're going to do 50 divided by 30. Okay, we see that that's 1, so 50 minus 30, okay, we have a remainder of 20. Okay, so now what we're going to do is we're going to take that 20 now, and now we're going to divide it by 30. So notice how this number moves, and the 30 now goes on the inside. So 30 divided by 20, we have 1. And then 20 times 1 is 20. So now we have a remainder of 10. Okay, so now we keep going. So now we bring the 10 over, and 20 goes on the inside. So now we look at 20 divided by 10, we know is 2. So now we get no remainder. And we look at the last divisor was 10. Okay. So when the remainder is 0, the final divisor is the GCF. Okay. Now let's take a look at applying Euclid's algorithm to find the GCF of 30 and 45. So let's try another one. So again, we look at dividing the larger by the smaller. Okay, so again, we see that 45 divided by 30 is 1. Okay, we're left with a remainder of 15. Okay, so now we bring the 15 over, and divide that by 30. So 30 divided by 15 is 2. Now we see that we have no remainder, so that means 15 is the GCF. So we say GCF of 30 and 45 is 15. Okay. All right, so now let's apply this knowledge to some larger numbers. Okay, so now let's take a look at the GCS of 96 and 144. So again, 144 would go on the inside. When we divide that out, we see that it goes in one time. 144 minus 96. Okay, we have a remainder of 48. So now let's try 48 as the divisor. Okay, 96 as your dividend. Okay, so 48 goes in 2 times. 48 times 2 is 96. So we have a remainder of 0. So 48 becomes our GCF. Okay. Now we take a look at even larger numbers, but the pattern will stay the same. So we have 660 on the outside, 840 goes on the inside. Okay, so 660 times 1 gets us 660. Okay, we have a remainder of 180. So now we bring over 180 and divide that into 660. Okay, now this is going to go in 3 times, because I can think about this is almost 20, that's about 60, so we're going to do it 3 times. Okay, and that's 540, 0, 16 minus 4, oops, 6 minus 4 would be 2, 5 minus 5 is 0. Okay, so now we see that we have our remainder, so now we're going to bring the 20, okay, and divide that into 180. Okay, so now we have 180 divided by 120. We see that that goes in 1 time. Okay, we have a remainder of 60. So we keep going. So now we take our 60 and divide that into 120. Okay, and we know that 6 times 2 is 12, so we're going to have a quotient of 2. Okay, and now we finally get a remainder of 0, so we know that 60 is the greatest common factor. Okay, taking a look at one last problem here. Okay. The greatest common factor has many uses. Among them, the GCF lets us find out the maximum size of squares that cover a rectangle. When we solve problems like this, we cannot have any gaps or any overlapping squares. Of course, the maximum size squares will be the minimum number of squares needed. A rectangular computer table measures 30 inches by 50 inches, and we need to cover it with square tiles. What is the side length of the largest square tile we can use to completely cover the table without overlap or gaps? So in this case, we have, if we use squares that are 10 by 10, how many do we need? So if we set this up as 30, and this is 50. So we can think about using 10 by 10 squares. Okay. We can see that when we go to count them, we're going to need 15. Okay. Now, if these were a giant chunk of cheese in a factory, would it change the thinking or calculations we just did? No, it wouldn't, because you still have 30 by 50. Okay, now try letter C and do the exit ticket on your own before viewing the next video.